可以被当看。
Okay. So I'll start.
Yes.
Dear all, first I would like to thank the organizing committee for this opportunity to report our
Can
recent
you
work.
put that full screen? Just
That's a full screen.
yeah, make it full screen.
PDF.
Thank you.
Oh, okay. Sorry. I forgot that. Okay.
Very good.
My report today is about probing the neutron skin synchronous with free spectator nucleons in ultracentral relativistic heavy collisions. My main collaborators are Jun Xu from Tongji University, Jiang Yongjia and Chun Jianzhang from Stony Brook. In this slide, I will illustrate our research from the following part: the motivation, density distribution from the density functional theory, classification and excitation from by the minimum spanning tree algorithm and the Gemini model, respectively. Deformation and swing up coupling from the Sigma-Fock-Bogdubov model. The idea of this study can be illustrated by this cartoon, where we compare the zirconium and the ruthenium collisions. Zirconium nucleus has more neutron and hence a large neutron skin than ruthenium, shown here. In high energy heavy collisions, the spectator matter disconnected from the participant matter, especially in the ultracentral collision region, where the impact parameter B almost zero. In this region, most spectator nucleons originate from the surface, which are dominated by the neutron skin. So a large neutron skin leaves more free spectator neutrons, which can be measured by the VDC detector. This analysis is consistent with measurements of the star collaboration. They report that a significant enhancement of free spectator neutron in zirconium collision relative to the ruthenium collision, because of the large neutron skin of zirconium than that of ruthenium. So this gives us a hint that the yield ratio of free spectator neutrons produced in zirconium collision to ruthenium collisions may be related to the neutron skin, and the neutron skin is related to the air, the through parameter of symmetry energy by the density function theory. This provides a way to probe the neutron skin. Here we refer the transport approach of intermediate energy heavy collisions, where the cladding nucleus form a hot nuclear system. And after a period of evolution, the hot nuclear system forms many excited fragments. And these excited fragments needs to be de-excited by a Gemini model, which is a Monte Carlo model to calculate the de-excitation of the nuclear fragments. After the de-excitation process, we can get the final products, which can be measured by the detector. And this result from Zhitao Dai shows the de-excitation process largely affects the final results, especially in the medium mass number region. Different with a process in the intermediate energy heavy collisions, the excited fragments are from the whole hot nuclear system. In high energy heavy collisions, the excited fragments are formed only from the spectator matter, which are separate with participant matter due to the large beam energy. And these fragments move with the beam directly after the collision and can be measured by the ZDC detector after the de-excitation process. This is a framework of the approach. First, we employ the density functional theory to obtain the density distribution of the cladding nucleus. And then we use a Monte Carlo global model to simulate the collision process to obtain the information of the spectator matter. After some clusterization algorithm, we can get the information per clusters. Then we use test particle mass to calculate the excitation energy of every fragment. With this excitation energy and the angular momentum, the Gemini model is used to de-excite heavy fragments. In this way, we can get the final yield of the neutron and proton as a function of n charge. It should be noted that the free spectator neutron is a routine measurement in heavy collisions, but it is most used to estimate the event centrality or the reaction plan. Our study is first to use the free spectator neutron to probe the nuclear structure. Here we introduce the Skirm-Hartree-Fock model. From this Skirm nuclear force, we can make a Hartree-Fock approximation to obtain this energy density function. And with this energy density function, we can the single particle Hamiltonian can be obtained using the variation principle. Then we can solve the Schrödinger equation self-consistently to get the wave function per nucleon. And thus we can get the density distribution or some other information. There exists 10 Skirm parameters, T0 and X sigma and W0, the spin-orbit coupling strengths. Normally, their value are obtained from fitting the experiment data. On the other hand, we can use the energy density function to investigate the properties of nuclear matter. There are also 10 macroscopic quantities, include saturation density, the energy at the saturation density, symmetry energy, and its loop parameter. So in this way, we can establish a relation between these two sets of parameters by making a parameter space transform. A previous study shows the neutron skin synchronous depends mostly on the on air, the third parameter of symmetry energy, and slightly on other microscopic quantities. So we can change the value of air and keeping the other microscopic quantities fixed at their typical value. To get the different density distribution, and of course the different neutron skin synchronous. Normally we think air is greater than 30 and smaller than 90, shown as previous studies. But the PRX2 data gives a large neutron skin thickness of light nucleus, and the analysis of this data favors a large air, even larger than 100. So in this study, we considered two typical value of error, 30 and 120. Okay, we also consider the deformation, the effect of the deformation through the Schumacher-Fock-Bogleubov math using the deformed harmonic oscillator basis. The previous study from Chunjian Zhang and Jiang Yongjia shows that the ruthenium has a large bit 2 deformation and the zirconium has a large bit 3 deformation. With the Boole density distribution, we use two-component global model to fit the distribution of the charged particle multiplicity n charge. And this is a fitting result. Zirconium, ruthenium, and gold collision at Rick energy and lead collision at RC energy. Now we already have the total information, total this space information of spectated matter for every collision event. These spectated matter are further grouped into heavy cluster and free nucleons based on a minimum spanning tree algorithm. And this is a sketch map of this algorithm for nucleon close in the phase space with a distance smaller than 3 fermion and relative momentum smaller than 300 MeV/c are belong to the same clusters. These correlation parameters are fitted by the gold data. Then we use test particle mass with a simplified Schumacher-Fock energy density function to calculate the excitation energy of every fragment and also the angular momentum. With this information, we can use a Gemini model to de-excite the cluster to get the final neutron-proton ratio. On the other hand, for the spectated nucleons that do not form heavy clusters, they still have chance to coalesce into light cluster and include deuteron, triton, and helium-3. The formation probabilities are calculated according to the Wiggin function in their center of mass frame. And so now we have the total free spectated particles that can be measured experimentally. They come from these two sources. The de-excite from the heavy clusters and coalesce from the free nucleons. This is a distribution, density distribution obtained from the Schumacher-Fock-Bogleubov model. Include the zirconium, ruthenium, and gold and lead with different through parameter of symmetry energy, 30 and 120. It is seen that zirconium has a bit 3 deformation, ruthenium and gold have positive and negative bit 2 deformation respectively, and lead is a spherical one. In this study, we only consider the case of actual symmetry. This is a free spectated neutron yield of the gold collision, And this result shows the coalescence parameter delta max equal to 3 firm achieves the best description of the good data. This is the isospin symmetry of the spectator matter of zirconium and ruthenium collision as a function of n charge. And red one represents the large air and the neutron spin thickness. It is clear to say that the spin effect is great in ultracentral collision, which is consistent with the previous analysis. Here we make a prediction for the isobar systems. As expected, the large air this large yield ratio of zirconium to ruthenium collision, shown as the red band, where R equal to 120, and this band represents the uncertainties of the excitation process, and we can see here the result in the UCC region is free from these uncertainties. So we think the yield of free spectate neutron in UCC region, it could be a clean probe of the neutron spin thickness, and also the through parameter of symmetry energy. Here we also make a prediction of the neutron over proton ratio for different single collision systems. Here we can see that the isospin effect is more pronounced in for more neutron-rich collision system, especially in the lead collision. For deformed nuclei, we found the neutron skin has a special angular distribution due to the spin-orbit coupling. Here we define the angular dependent neutron skin. This distribution of the neutron skin is different for different W0, the spin-orbit coupling strengths. The blue line represents a weak spin-orbit coupling strength, W0 equal to 80, and the red one represents a strong spin-orbit coupling strength, W0 equal to 150. And the effect of the spin-orbit coupling is most pronounced in ruthenium and gold nuclei. For the reason why spin-orbit coupling affect the distribution of the neutron skin, we think it is that the nuclear spin-orbit coupling affects the outermost nucleons in the nucleus. Here is a simple diagram of the energy level, and this is the energy level without a spin-orbit coupling, and this is the energy level considered spin-orbit coupling. Let's use ruthenium for a simple illustration here. Ruthenium has a 44 proton and 52 neutron. It is seen that the angular distribution of the outermost nucleon in the open shells are most sensitive to the strength of the spin-orbit coupling compared with those in the those of the innermost nuclei in the closed shells, where the spin-orbit coupling strength almost no effect.
So Roma,
Also,
you need,
yes,
you have well, you're already in the discussion time, but it's okay.
okay. Um, uh, 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 okay, I will. So, regardless of the reason why spin-off coupling affects the distribution of the neutron skin thickness, due to these special distributions, we found the neutron over proton ratio is different in different collision configurations, such as the tip-tip and body-body collision. So we can come for a large W, especially for a large W0, the result is large in tip-tip collision than that in body-body collision, and for weak spin-off coupling strengths, the result is smaller in tip-tip collision and smaller in tip-tip collision than that in body-body collision. So we can compare the relative results of neutron over proton ratio in tip-tip and body-body collision to prove the distribution of neutron skin thickness and also the spin-off coupling strength of W0. Here is a summary. In this study we use yield ratio of free spectator nucleons as a probe of neutron skin and W0, the spin-off coupling strength. The advantages of this approach is that we focus on the spectator nucleons to avoid the complex dynamics, and the free spectator neutron are easily measurable. We use a Schermatty-Fock Wolf model to make a self-consistent spherical and deformed calculations to establish the relation between neutron skin thickness and the pseudo-parameter of central energy error instead of the Saxon form. We focus on the UCC region, where the result is free from the uncertainties of de-excitations. We take a ratio of neutron rich and to a neutron pro system to reduce the experimental and theoretical uncertainties. Moreover, we found the neutron over proton ratio is also an excellent probe of neutron skin, and for a single collision system, especially in the neutron rich collision system such as lead collision. We also found the different W0 leads to different neutron skin thickness distribution, and that leads to a different neutron over proton ratio in different collision configurations. So that can be a probe of W0. The reason why spin-off coupling affect the RMS radius of outer, we think it is because the spin-off coupling affect the RMS radius of the outer nucleon, and this nucleon contributes significant to the angular dependence of the neutron skin. And we think this phenomenon should be general in different approach. In this study, the Schermatty-Fock model and also the IMF model is still ongoing. Okay, thanks. That's all my report.
Thank you for the talk. So we have 5 minutes for discussion. Yeah.
I have a brief question and then a small comment. So the question is related to the spin orbit coupling. Do you just have one parameter controlling this, or do you have scalar isovector term that's present in some energy density functions?
We compare this 10 microscopic quantities include the S vector or S scalar interaction. We found the spin-off coupling has the most phenomenal effect on the neutron skin distribution. Yes.
So you just have the one parameter determining the spin orbit coupling in your
of course, the distribution of the neutron skin affected by other quantities, but in our test, the spin orbit coupling is the most phenomenal one.
Okay, and a brief comment, whenever you're doing a sensitivity study like varying L, for instance, there are a series of forces that vary L and fix it, and then constrain it to the available data so that you don't have crazy binding energies for no nuclei. So that would probably be more robust way to do things so that you don't have wild descriptions of lead and oxygen and all this stuff.
So your comment is that there's some way to improve it?
Yeah, well, instead of just varying the L, for instance, and not changing any of your other parameters, there are a series of forces where people have fixed L at different points and then reran the fitting procedure. So this leads to, let's say, a more consistent description of other nuclear groups. The series of forces are the SB series.
Do you understand the comment? You do here? Here.
I can put it in the document.
Yeah, please.
Okay.
But in his approach, the density functional they use is this they call it's a little bit different, right? Because their parameters are a combination of many other parameters, so which are they claim at least, which allow them to change L only because the other parameter will be automatically changed because it's a combination.
The others are changed, but
Yeah.
they're not, if they're not refit, if you check your binding energy for lead, for instance, I'm sure it'll vary. By a lot.
Yeah, please enter the comments. Maybe here Lumi can answer the question. There are more. Yes, go ahead.
I have a nice question that how do you extract the microscopic properties like the L values from your EMT theories? Is there a simple way to explain that?
Sorry, I don't understand.
So I want to know that how do you calculate the microscopic properties from your EMT theories?
Yes, we use these 10 microscopic quantities, and we found the neutron skin thickness depends mostly on the through parameter of symmetry energy, and slightly depend on the other microscopic quantities. Do you mean that?
Thank you.
Sorry, I don't very understand. So maybe we can talk after this. Sorry.
Sure.
Okay, so I don't see any more questions. So let's thank Lumen.
Okay, I will quit the share.